Yeah, hello friends. Welcome to Physics Online. So, how are you doing? Hope you are all well. We are starting with electrical field. Now, first we look at the broader concept of field. So, a field is a region or space at every point of which there exists a physical quantity associated with it. That means if you look at a broader space, suppose in your room, and your fan you have switched it on. Now at different places in your room, if you sit, you will feel the breeze coming from the fan at a different strength and at a different direction. Okay, so your room where you are sitting with the fan on can be said to be a vector field. Let's move on to another type. So let us say that your fan is switched off and you have put on your AC. Once again, if you sit at different locations in your room, the temperature or the hotness or coldness that you feel at any point will not be the same. In other words, the temperature will not be the same. So every point will have a temperature. So it's basically a scalar field. That means here we are associating with the temperature, which is a scalar. In the previous case of the fan and the breeze that you are playing is a vector field because there was a direction and the strength of the breeze. Okay. So once again repeating, a field is a region and it's a space at every point of which you can associate a physical quantity with that field. If the physical quantity, like in the case of your fan, is a vector, then you will feel the vector field. That means we are given an example here, something E depends on x, y and z. So if you put x equal to 1, 2, e at 1 comma 1 comma 1, then obviously you will get the field as 1 I comma j comma k, correct? So let's take an example over here and say that we are trying to find out the value of E at the point 1 comma 2 comma 3. So according to its definition, first case you will get 1 into 2 into I, plus then you will get 2 into 3 into j, and then you will get 3 into 1 into k. So ultimately you will get a vector which will be 3i cap plus 6j cap plus 3k cap. Let's take another example of the same. Let's say the E is there, but this time we are taking it as 2, 1 and minus 2. So in this case it is xy, so it will be 2 into 1 into I cap plus the next one is yz, so it will be equal to 1 into minus 2 into j cap, and plus you will get x into z, so it will get 2 into minus 2 into k cap. So your answer will turn out to be 2 I cap minus 2 j cap minus 4 k cap. So did you understand? That is the value of E depends on that thing, and it is a vector because it is given in terms of I, j, k. I suppose I made myself very clear. Once again, let's look at a next example. Now the physical quantity that we are talking about here is a scalar quantity, correct? So it's called a scalar field, as you can see over here. Let's again look at some examples. So let us say that the value we are looking at is equal to 4 comma 3 comma 1. So your V as defined over here will be square of 4 plus square of 3 plus square of 1. So will turn out to be 16 plus 9 plus 1. So it's a quantity 26. So it's a number. So therefore it is a scalar quantity. So understood scalar field and vector field. So now let's go to other field we are interested in. So we talk about electrical field. Okay. So we talk about electrical field. So electrical field is a space or region at which there exists a electrostatic force. Now when we say electrostatic force, that can be experienced only by a charge placed at that point. So suppose you have a place, and at every point the moment you place an electron, a proton, anything that has got charge, and it automatically is subjected to a force, such a place is called a electrical field. Now, to measure the strength of the electrical field, we have given a new physical quantity called as electrical field intensity. Of course, it's a vector quantity because it is associated with the force. Now, remember, in most of the exercises or most of the dialogue that we are going to have ahead, the electrical field and electrical field intensity will be used more often in same terms. But remember that electrical field is a physical quantity, whereas electrical field intensity is a unit that we have decided to incorporate. So, coming back to it, electrical field intensity at any point in an electrical field is defined as the force experienced by a unit charge, namely 1 coulomb. So, if there is a electrical field and suppose that a charge of 5 coulomb, a charge of 5 coulomb. So, here we have placed a charge. So, let us say that the charge is 5 coulomb and it experiences a force of 20 Newton. Then the electrical field at that point will be equal to 20 divided by 5, and of course it will be positive, so it will be in this direction, so it will be equal to 4 Newton. Okay. So this is what is the meaning of electrical field intensity. It is measured in Newton per coulomb. As you can see, we have force in the numerator, charge in the denominator. Of course, later on when we look at potential, we will also describe the same field or the unit of the field as volt per meter. So going ahead, we can also say that force can be written as charge into electrical field. So first thing we need to note is what would be the electrical field due to a point charge. To study that, we have taken a space point O in space, and we have kept a charge Q there, and we are looking at the electrical field at P. Now, as in the definition of electrical field itself, to know the electrical force, you need to have a charge Q. So keep a test charge Q. By the meaning test charge is that Q is much smaller than capital Q. So consider a charge O, consider a point O in space and let a charge Q be placed there. We intend to find the electrical field at the point P due to charge Q. The point P is at a distance r from O. So to find the electrical field at P, we bring a small test charge Q and place it at P. Now we know how to find the force because that is given by Coulomb's law. So F will be equal to 1 upon 4 pi epsilon naught capital Q small q upon r square, and this unit vector r shows that it will be in the direction of r, both of them being positive. Now going back by the definition of electrical field, we know that electrical field will be equal to F upon Q. Putting the value of F over here, we get electrical field will be equal to 1 upon 4 pi epsilon naught Q upon r square. Again it will be in the direction of r. So this is the general expression for electrical field due to a point charge. So now a very simple example. Okay, suppose you have a charge 8 coulomb and we have a point 25 centimeters from that coulomb, that charge, and we want to find out the electrical field. So we use the simple arithmetic formula. We already know that 1 upon 4 pi epsilon naught is written as 9 into 10 raised to 9. Put the value of Q, put the value of R, and you get something like this. You could also write the unit as Newton per coulomb. Now, if a charge of 20 microcoulomb experiences a force 1.2 Newton. Now here you are given the force and you are given a charge. We have already done this exercise earlier. So electrical field is force upon coulomb. So 1.2 upon the charge will give you this much electrical field intensity. Now let us say that we are given an electron whose mass is given, whose charge is given, and it's placed in a uniform magnetic field. Uniform electrical field means everywhere the electrical field is same. We will discuss about uniform electrical field as we go along. We have to calculate the force acting on the electron and the acceleration of the electron. So see, force is E into capital E. E is the charge on the electron, E is the electrical field that is given to you. Key in and you get this force. To find the acceleration, we divide the force by the mass and you get the acceleration. So suppose there are many charges in that space. There is charge q1, q2, q3, and they're not all same. And some of them are positive, some of them negative. It also shows how the electrical field will be. If the charge is positive, electrical field will go away. If the charge is negative, the electrical field will come towards the charge. So now there are 4 charges over here shown, q1, q2, q3, q4, and each will produce an electrical field E1, E2, E3, E4. The net electrical field at P will be the vector sum of electrical field of all the charges. So this is superpositioning of electrical field. So the introduction to electrical field we have finished now. In the next part we will show how to describe electrical field visually or schematically or in the form of a diagram. How will you show an electrical field? That will be electrical field lines. And then we'll look at how a positive charge looks, how a negative charge looks, what happens if you keep a positive negative charge, and so on and so forth. We'll also go to see what is a flux of an electrical field. Till that time, thank you friends for joining me, and you will all will joining in the next session. Thank you very much.